liftoff of the Delta rocket carrying Blast.
Hello, my name is Melissa Burkhead, and I'm about to present a video that can work with 6th through 10th grades quite nicely. So I can share. I'm just going to share my screen at this time. Let's see where we can go. Let's just share the desktop. And I'm going to let that happen.
So before we do that, I would like to welcome everybody to Discovery Festival 2021. Today we are on the last day of the first week of this awesome festival. We have a really special guest by the name of the National Math and Science Initiative. And they are going to be doing some awesome demonstrations for you today. And at the end, we will go ahead and take questions and answers. We'll take questions and we'll give answers. So looking forward to it. And I'll hand it over to you, Melissa. Thank you. All right, it looks like we're having some technical difficulties, and it looks like Melissa's back on. She will share the video shortly.
Yes, I'm just making it extremely interesting for us. Thank you all for your patience. So the first thing we'll do is watch this video, and I will be, my understanding is that you all can see that. And I also will be checking things out in chat. If we do have participants who would like to chat questions, I can answer them. Or at the end of the video, we will answer any questions that you might have. So my understanding is that we'll watch this video.
Box it up. This lesson provides a hands-on approach to constructing an open-top box with maximum volume. Using both square and rectangular sheets of paper, students cut squares from the corners of the paper and fold up the sides to create the boxes. Recording the dimensions and volumes of the resulting boxes in tables, on graphs, and as equations helps students analyze the volumes and generalize their relationships. My name is Melissa Burkhead, and I look forward to walking you through this Box It Up lesson today. Let's get started. Make certain that we have these materials before we begin. You'll need your student activity pages, and those activity pages provide instruction and documentation of the tabular, graphical, and symbolic representations that we will be exploring today. You'll need some tape, you'll need scissors, you'll need a ruler or index card that could be used as a straight edge, and you'll also need one piece of 8.5 inch by 11 inch paper. That's a regular sheet of paper. Let's start with looking at the activity sheet. We're going to do number 1 on this activity sheet together. I will model part B, and I have emailed students to complete parts A and C, and we will look at the data that they provide. So the instructions state, use square pieces of paper as described to form open top boxes by carefully cutting congruent squares from each corner. Let's stop there. What do we mean by cutting squares from each corner? So let's start off with a square, and the activity is encouraging us to cut out squares from each corner of our large square to create an open topped box. So first we would need to draw our little squares on each corner, and here is a little example where you can see some squares that were faintly drawn. And then for time's sake, I'm not going to have you watch me cut out those squares, but if I were to cut that square out, that square out, that square out, and that square out, I could fold these flaps. And after I fold these flaps, I would tape them. But do you see how that creates a pretty cool, nice little open topped box? So I want you to get that into your head, and then let's take it a step further and really begin to think about trying to fill that box, which would mean trying to find the volume of that box. Let's go to number 1, unbox it up. Remember, you're to use square pieces of paper, and you are to cut out squares from each corner. And the square side length will be determined for the corner pieces by the height of the box column. Now, students are going to be in charge of, each student is going to be given one height of a box and a defined 6 inch by 6 inch or 4 inch by 4 inch square to create, and the student's going to have to identify the length of the box, the width of the box, the height of the box, which is given, and the volume of the box. Now I'm going to do that for B with the 5 inch by 5 inch box. And that's due to the fact that we're going to have to use a ruler, and we'll be thinking of 2/3 of an inch, and I'll help you just consider working with fractional representations and the task at hand. So let's begin with our 5 inch by 5 inch square to form a box. So now I am going to do one part B, and I'm going to fill in for these 5 different boxes. Each student will be in charge of just one, either in part A or part C of the problem. So the reason that I'm choosing part B to model is because some of my heights of the boxes require a little bit of fractional thinking, and I thought that I would take care of that to give you a little bit of guidance. So we're using a piece of paper that's 5 inches by 5 inches to form our box. And remember, from the modeling of the problem, the height of the box was the side length of the corner squares that we cut from each corner of that square. So if the height of my box needs to be 2/3 inch, I'm going to be cutting out 2/3 inch side lengths of squares. Now, in your activity pack, you also received the handy dandy ruler. And this dandy ruler is helpful because it's also divided into 12ths. And that's really going to be quite help friendly in the sense that some of our side lengths are fractional representations, and having things in twelfths will aid our situation quite nicely. In fact, our first example, which is 2/3 of an inch, we have to think about, okay, what's 2/3 of an inch and how would I mark this on the ruler? Well, again, each tick mark represents 1/12 of a unit of that inch. So I just need to be thinking of 2/3, and I want to put that into twelfths, right? Because I'm just working with 2/3 of 12/12ths of an inch. So what times 3 equals 12? 4. 4 times 3 is 8. So I'm essentially going to count 8 tick marks in this situation to get my square. So I'm going to show us how we're doing this just because I think it's going to be helpful in the modeling situation here. So this was 6, 7, 8. So I'm going to put a little mark right there. And then I'm going to think about some geometry and drawing a very parallel line to this line on my square. And then I'm going to go here and I'm going to look for that 8 tick marks. And I'm going to make this little mark. And then I'm going to take my index card, or you could have a ruler, a straight edge, what have you. And you want to try your hardest to draw a line that is extends, and that line is parallel to this side of the square. And I'll do that over here. I'm going to extend, and lo and behold, I get that square. So I'm going to cut that square out. And then I need to do this 3 more times. I'm going to do it 1 more time with you all, and then I might use the power of video. So I'm going to my 8 tick marks. And this time I'm just going to go a little bit backwards here and draw that. And then I'll go here and I'll count 8 tick marks. Looking good. All right. And so again, I'm taking advantage of some geometry. I want to draw the line that's parallel to this side of this square that goes to that point there. And then I want to draw this horizontal line that goes through that little mark. So then I'm going to continue doing that in my other corners. And so I'm going to come back after I've cut out my squares. So here's the final product once we have cut out the 2/3 inch side length squares. And you can see that you fold this up to form a box. Now I am going to use some tape and make my box sturdier, but I think that I still want to keep the situation looking like this to fill out my information, because I really want to make certain that I understand exactly what are we referring to when we're talking about the height of the box, or the width of the box, or the length of the box, or the volume of the box. So I think that we really want to remember that we started off with a square that was 5 inches, and then we cut out these squares, and that's 2/3 of an inch, and that's 2/3 of an inch, okay? So what we're referring to, the height of the box, is that 2/3 inch. The length of the box is referring to the length of the base of the box. So I'm hoping that we're seeing that we're just taking 5 minus 2 times 2/3. So I'll have this length of the box is 5 minus 2 times 2/3, and that entire quantity is in inches. So 2 times 2/3 is 4/3. So 5 minus 4/3, well, that's like 15/3 minus 4/3 inches. So that's going to equal 11/3 inches. So that means the length here is 11/3 inches. The width, well, we're working with a square, And does it make sense that our width is going to be equivalent to our length? So that 2 is going to be a 5 minus 2 times 2/3, which is 11/3 inch. So the width here is 11/3 inch. Now to get the volume, we're taking the area of the base, which would be 11/3 inch times 11/3 inch times the height. So we have 11/3 inch times 11/3 inch times the height, which is 2/3 inch. And that's going to give me a volume. 11 times 11 is 121 times 2. Well, that's going to be a whopping 121 times 2. So that's 242. So 242. 3 times 3 times 3 is 27. So, and that's going to be inches cubed. So I get that beautiful, beautiful volume to be 242.27 inches cubed. And that's approximately, we'll get 8.963 cubic inches. Okay, so are we understanding how the pieces of our box correlate with these different values? Let's take a look at our next height. Now, the next height that we're going to work with is 5/6 of an inch. And how are we going to do our counting with our ruler? Well, remember, each tick mark is 1/12. So 5/6 is equal to how many 12ths? Well, 6 times what number equals 12? 2. So 5 times 2 is 10. So I need to count off 10 tick marks, 10 of my 12, to see where I can get a height of 5/6 inch. So I'll go over here and I'll use my ruler. I'm getting a little, okay. And we'll progress from here. So I'll line this up and I'll go. I know that my halfway, the half inch is 6/12. 7, 8, 9, 10. That's 10/12, which is 5/6. And then I'll go here, and that's 6, 7, 8, 9, 10. So I need 10/12. So I can draw this little mark. And then I'll take a straight edge and try to get parallel to the side. I'll try to draw a horizontal line here. A little hard on the board, but we can get this going. So I'll extend as shown. Then I'll draw a vertical line that goes through this point. I want to make sure it looks a little bit more vertical than I'm drawing it. But you do want to pay attention to this. So that's why I'm trying to be neat. So there's my square that I'll cut out. And then I want to do that. I'm going to do that 3 more times. I'm going to do it 1 more time with the group because I do want to show that we want to make sure that we understand what's happening. So that's 6, 7, 8, 9, 10. So right here. And then I'll go here and 6, 7, 8, 9, 10. Okay, then I'll draw my vertical line. And I'll draw my horizontal line. And then I want to do that in my other 2 corners, just as you will be doing with the example that with the student will be doing with the example the student has been assigned. So I'll come back with a finished product. Now we see a box that has been cut from a 5-inch square that has the squares that were cut out were 5/6 inch inside length. So let's think about how that's going to affect the length of our box and the width of our box. You can see from the product that the base of the box is a square. So our length and our width should be the same. Remember that we started out with this 5 inches and then we cut off 5/6 inch here and 5/6 inch there. So the length of the base is just going to be 5 minus 2 times 5/6, and that's going to be in inches. And if we wanted to simplify that, this would be 10/6, which is 5/3. So 5 minus 5/3 inches. Well, that's 15/3 minus 5/3. So that's going to simplify to 10/3 inch, 10/3 inch. So that means the length of the box is 10/3 inch. The width of the box is 10/3 inch. The height of the box was 5/6 inch. So to get the volume, we take the area of the base of the box, which is 1/109 inch square, times 5/6 inch. And that's just going to yield us that 250/27 inch cubed. And that's approximately 9.259. And that's cubic inches. Okay, 9.259 cubic inches. Our next box is to have a height of 1 inch. And I've already built that one because I think that you're now feeling comfortable with how the boxes are generated. Well, and if I have a height of 1 inch, I take 5 minus that 2 times 1. So 3 inches would be the length of the box here, 3 inches. And the width would be 3 inches. And the volume, well, 3 inches by 3 inches by 1 inch, that's 9 cubic inches, okay? The next example has a height of 1 1/6 inch. So 1 1/6 inch, that's the same thing as 7/6 inch. And I do my calculations. I get a length of the box to be 8/3 inch, a width to be 8/3 inch, and the volume would end up being 224/27. 224/27 inches cubed, and that's approximately 8.296 cubic inches. And then my last box in this situation had a height of 1 1/3 inch. Well, that's going to yield a length, because we take our 5 minus 2 times 4/3 inch, we would get 7/3 inch. Our width is 7/3 inch, and our volume would end up being 196/27 inches cubed, and that's approximately 7.259 in cubic inches. So we have a collection of all 5 of our boxes, and we can think about, I wonder which one is the largest, which one holds the most volume. That might be a question that comes down the pike. But let's look at this tabular data because I see some patterns generate. Here, my length of the box is 11 inches, 10 inches, 11/3 inches, 10/3 inches. Well, that's 9/3 inches. That's 8/3 inches, 7/3 inches. Interesting. I wonder what's happening here. Notice our volumes. Where do we have the greatest volume? It appears that a height of the box of 5/6 inches yields the greatest volume in this situation. I wonder what's going to happen when you send in your data. So each student will be assigned either to work from a 4-inch square or a 6-inch square, and you'll be given a specified height. And pretty soon we'll come back with that data. Students now have sent in their findings when they were assigned one of the boxes to create, and they had to find the length of the box, the width of the box, and the volume of the box. So I've compiled all of the data in the table, and we can begin to look at it. So the first is 1A, where we're showing a square piece of paper that's 6 inches by 6 inches. And we look at a wonderful pattern here. We're incrementing by 1/2 inch on the height, and the length of the box is actually going down, decrementing by 1 inch. But the volume, let's look, it appears the volume increases and then begins to decrease. We'll make note, looks like the maximum volume in this situation is 16 cubic inches. Maybe we'll use that a little bit later. Let's go back to the second example, and this was the one that we worked with previously. Here, the height of the box is, it appears, is incrementing by 1/6 of an inch. And notice we have a pattern, 11/3 inch, 10/3 inch, that's 9/3 inch, 8/3 inch, 7/3 inch. So we see some beautiful patterns here. Now, many of us aren't too familiar with what these fractions are equivalent to. So I've found I've found approximations using a calculator. It looks like 9.259 cubic inches is the maximum volume in this case with this given set of data. And then the third set was another set in which the students were assigned to provide the length, width, and volume of the box. And students were given a 4-inch by 4-inch square with which to start. And in this instance, it appears that we are incrementing again by maybe 1/6 an inch. But again, you see this beautiful, nice, fun pattern, 10/3 inch, that's, I guess, 9/3 inch, 8/3 inch, 7/3 inch, or 6/3 inch. And then do we see a maximum volume in this situation? Well, it looks like the volume increases and decreases. That pattern continues. And it does appear that this approximately 4.741 cubic inches is yielding a maximum volume with the given information provided. Okay, to let you explore number 2 on your own. And then we'll move on to number 3 for more modeling. On number 3, we have use an 8.5 inch by 11 inch piece of paper to form an open top box by carefully cutting congruent squares from each corner. Use only whole number values for the lengths of these squares. The length of the box will be formed from the 11-inch side, and the width of the box will be formed from the 8.5-inch side. So I'd like things to follow what we did in the previously, but notice that our length and our width are going to be different because we're starting off with this 11-inch by 8.5-inch piece of paper. So we're going to have a little different box. Our box's base will be a rectangle and not necessarily a square. So here, let's think about this a little bit more. We are from the problem stating, we want to have heights that are whole number values. So I'm thinking this could be 1 inch, and then 2 inches, and then 3 inches, and then 4 inches. Now, when I'm in school, I try to fill in all the blanks, but when I do 5 inches, I'm actually taken aback because think about that. If I do 5 inches, I'm putting a question mark by that. Imagine taking 5 inches here. So I have a ruler and I go 5 inches. That's more than half of 8.5. So I would be cutting into some interesting space. So that's why we're going to stop at 4 inches. And this is a great example of sometimes you don't fill in all of the cells. So I'm going to build one. I will build let people build and email in your findings. I'll go with the 1 inch box. So I go over to my corner here and I'm going to find 1 inch so that you'll remember me doing this earlier. And then I'll find another inch here. And then I'll extend these. And I really want to try to be parallel to the length in this situation. And here I want to try to be very vertical, okay? And then I'll do that down here. So I'll go 1 inch. And notice there are a few ways you can do your measurements. I'll extend this. I'll go 1 inch here. And I'll try to make this vertical line. I'll try to make this vertical line. I'll try. And then I'll try to make this horizontal line. Guess I could do some more math with you. I'll draw a line that has slope 0. I'll have a slope that's undefined. And then we'll continue on. I'll go over here and do these 2 corners and cut this out. And let's take a look at the product. Here is our box in which we cut out a 1 inch square from each corner of the rectangular 11 by 8.5 inch piece of paper. So we need to calculate what will be the length of our box and the width of our box, as well as the volume of our box. So remember here, we started out with an 11-inch side. And on this side, I cut 1 inch. And this side, I cut 1 inch. So this inner rectangle would have length 9 inches. I'm hoping that makes sense. Then we would have the larger rectangle had this distance here from this point to this point was 8.5 inches. And I cut off 1 inch here. And I cut off 1 inch here. So 8.5 minus 2 is 6.5 inches. So this here would be 6.5 inches. And remember, my height here is 1 inch. So I don't know if you can see that, but I have that that's 1 inch, 9 inches, and 6.5 inches. So let's input that on our table. So the length of the box here was 9 inches. The width of the box was 6.5 inches. And the volume, well, we would take 9 inches times 6.5 inches times 1 inch, and that yields me a 58.5 inches cubed. Now I'm going to check my email to see what the groups are providing in giving me the length, width, and volume of the box. One group has a height of 2 inches, another group has a height of 3 inches, and the other group has a height of 4 inches. So thank you for the data that was brought in here. It appears that with a height of the box being 2 inches, the length of the box was 7 inches and the width of the box was 4.5 inches. And we get a whopping volume of 63 cubic inches. For the group who turned in a height of 3 inches, you see a length of 5 inches and a width of 2.5 inches. And we notice that the volume of that box, we would just be taking 5 inches by 2.5 inches by 3 inches, and we get 37.5 inches cubed. And then our last example, a height of 4 inches, the length of the box would be 3 inches. The width of the box would be 0.5 inches. I'd really like to see that box. And its volume it's not going to hold a lot of Jell-O, 6 cubic inches. Now, for part B, we're going to look at things graphically. In this example, we looked at things tabularly. Well, it states graph the data using the length of the cutout as the independent variable and the x-axis, and the volume of the box as the dependent variable. Because does not the volume depend on the length of the square that one cuts out? Instead of filling that out, I'm going to go to a graphing utility. So here is our data. This is the same thing that we would be plotting over here. This length of a cutout square is our independent variable, and our volume is the dependent variable. So I'm going to add some data, and I'm going to make my independent variable along my horizontal axis. So that's the length of the cutout square. And then I'm going to make my dependent variable the volume. And so here we look at that data, and we might then make a generalization from that data by going to subsequent pages in the activity. All righty. So now let's move on to C. We've looked at things tabularly. We've looked at things graphically. The length of the side of the cutout square becomes which dimension in the resulting box? Well, that's the height of the box. What is the largest square with whole number dimensions that can be cut out? Well, we discussed that earlier. We discussed that that would have to be 4 inches. And that was because we were working with an 8.5 inch by 11 inch rectangle. And 4 times 2 equals 8 if we went with a larger square, we could not make the cut. Now for E, of the boxes in your table, what are the dimensions of the box with the least volume? What is the volume of that box? Well, the least volume was that 6 cubic inches, and that gave me a length of 3 inches, a width of 0.5 inches, and a height of 4 inches. The volume was equal to 6 cubic inches. For F, of the boxes in your table, which of the dimensions of the box has the greatest volume? What is the volume of that box? Well, it looks like we have the greatest volume with 63 inches. So that was a length of 7 inches, a width of 4.5 inches, and a height of 2 inches. Our volume was equal to a whopping 63 cubic inches. On G, using the length of the original paper, 11 inches, and the height of the box H, either explain how to determine the length of the box or write a rule for determining the length of the box. So we're looking here at an 11 inch by 8.5 inch rectangle. Agree? And what we're wanting to do here is we're wanting to explain how to determine the length of the box or write a rule for determining the length of the box. So our H is the height of the box. So remember, our H is the side length of our square. Agree with me on that? So each of those is an H. So the length of my box is going to equal 11 minus 2H. Okay, that could be our rule. Now for H, we have using the width of the original paper, 8.5 inches, and the height of the box. Explain how to determine the width of the box or write a rule for determining the width of the box. So I can say the width of the box is equal to that 8.5 minus 2H. Now for I, we are to write an equation for the volume of the box in terms of the height of the box. Well, we could take the area of the base of our box, which is the length times the width, and then multiply that by the height. So the volume would equal this 11 minus 2H times 8.5 minus 2H times H. And that looks pretty darn excellent. So now for J, only whole numbers were used for the square cutouts of the boxes in the table. There are other boxes with volumes greater than any of these. Determine the dimensions of the volume of the box that will be greater than the ones that have been built. Plot this data on your graph in part B. Show your work. All right. Well, we could try to plot our function. That's one thing that we could do here. So what if we went back to our data here and we could take a look. This might be a little too spicy, but hey, we might as well go for it. We could go to essentially here into statistics and do stats calculation. And what if we did a cubic regression? Because if you look at our volume function, we have a cubic function. So I'll go to my cubic regression, and my X list is going to be my length of the cutout squares, that independent variable. My Y list is going to be the volume of the box. I'll store that in F1, and then we can click OK. So here is our regression information. Now I could just add a graph, and I'm going to go up to my function, and lo and behold, here is a graph of my function. Maybe I need to take a look at my window. Maybe in window settings, I'll go and I'll make my Y. Let's make my Y 90. And let's make my X. Remember, we're needing to maybe run, we can have a -2. And I don't need anything past, my 4, but we'll just look at 5 and take a look here. And then take a look. Here we have a piece of our function, and we can clearly see that the volume increases and then decreases. In fact, I can go here to geometry, and I can take a look at point on. I'll put a point on this graph, and it appears that we had that 63 when our volume was 63. We had a 2-inch square, right? So I'll do my 2-inch square. But notice your 2-inch square is over here. So I can move toward my max, and it looks as if I'm going to have a max more or less around 1.552, 53. So that might be a way to approach this problem. So that gives you something to consider as we plug through this. The actual answer would be to cut out a 1.585-inch square corner, and the maximum volume would be 66.148 cubic inches. Now, we've traveled a long way in this exploration. It's been so fun boxing it up with you. We started with some sheets of paper that were squares, cut some other squares off of the corners, built 3-dimensional boxes, and really explored some interesting volume implications.
All righty.
Awesome.
Thank you very much.
Well, thank you very much. That was very interesting, and especially when you graphed it at the end there and put it in those perspectives. So I really enjoyed it. I hope the teachers and students have. And we actually have a few questions if you're ready. So so the first question is from a teacher, and she is out of Albuquerque, and she is asking, can this be adapted to younger students?
Definitely. I think that the main thing that you could do is have the students definitely cut out the boxes and do the measurements. I think that the students at the younger ages would benefit from not trying to calculate the base length of the box, the base height of the box, as much as actually measuring that. So I'm thinking that what I would do is you could still model it, and I would model it with that middle example with the 5 by 5 inch square, but then have the students build the boxes and with their rulers do measurements and come up with a decision or with a consensus on what value the class would like to enter into a chart as their base and their height. It's an excellent question.
Great. And she also asked, is there any curriculum leading up to this exercise that would be helpful?
The curriculum, the leading, well, this was done with my students. I've started doing this activity in 2020 when we were shut in. And this was right after we had explored area and volume. So it was an activity that we were doing after students had had exposure to area and volume.
Great. So the next question is coming from a high school student by the name of Catherine. She is wondering, how did you develop this exercise?
Hi, Catherine. This exercise is available to anyone who is interested in the National Math and Science Initiative's activities. If you were to go to NMSI's website, I think that you could just do a Google for the National Math and Science Initiative and check out Laying the Foundations. This is one of the sample lessons. During 2020, I was looking for some preset lessons, and this really worked well with my ninth graders as we did this virtually. It really was important that the teacher modeled the experience. I felt like watching this again, I felt like, okay, I think that we're showing many examples, but that paid dividends because the students just ate it up. And so you can find some activities like that on NMSI's website.
Great. And we encourage all teachers and students that are participating in this to go onto their website and check out the awesome materials that they have. So the next question we have is specifically just about, what they learned in this volume exercise. So the question is, how do we carry this into everyday life?
Well, how I want my students to carry this into everyday life is that I want, number one, I want the students to pay attention to multiple representations. I'm hoping that from this experience, there was a physical experience that we took part in, but then we tried to work with problem solving at an analytical level where we came up with numeric representations. And then to make our decisions on when we would have our maximum volume or when we would have, to find that maximum volume, what we would do is we would look at graphical representations and the numerical data. And it's just amazing. You want to take into account that even though you're cutting out your square side lengths, and that might be increasing, your volume does increase, but then it begins to decrease. There's this optimal point. And so what I want my students to realize is you want to inspect the data and make informed decisions. And that when we do mathematics, because a lot of my students think mathematics is just taking their pencil and paper and grind. No, we want to explore mathematics physically, graphically, numerically, and analytically. Because number one, you have so many different types of learners, and you're going to have a stronger argument if you've looked at all those perspectives. Now, I can give you a wonderful how we use this in real life. Think about the fact that we might want a maximum volume on a box, but we might want minimum surface area because the surface area would be the materials that would be made, that we would have to provide to make the box. Or we might want something vice versa. In manufacturing, that is extremely important. If we think about right now with inflation, manufacturers are thinking, okay, I have people who can only spend $3 for a box of cereal. How can we design this so that they are able to get a volume of cereal, but both of us, the people can be fed, but also manufacturing companies can continue to exist.
Wow, that's an awesome example, and it shows how math can be used to reach goals and help companies be able to deliver their products to people. So there's another question that's kind of similar. I mean, you gave a really good real life answer, but if someone likes this math, what career should they consider, or is there maybe any advice you would give to a student that's enjoying this math? What kind of path would you encourage them to go on?
That is a spectacular question. And the answer is engineering. And engineering has opened up into so many different facets. There will be students who are engineers who might not be able to calculate that well, but their design skills are amazing and they're still using mathematics. It's that multiple perspectives that are out there for mathematics. So check out engineering, because and I'm still amazed when I talk to my students of the different types of engineers that are out in different types of engineering degrees that are out there. People who have artistic abilities can shine in the math world and the engineering world.
Great. And what kind of advice would you give to students that maybe struggle with math?
I would, number one, don't try to compare, don't try to use someone else's standard as your standard in understanding mathematics. It goes back to the multiple perspectives. Find out how you learn best. If you need to draw a graph or come up with a visual representation before you begin calculating, do that. And talk to your teachers. Your teachers are thinking about you and your success all the time. And they have a lot of experience and perspective. So that's my best advice.
I think that's a very good advice. As a student myself who struggled with math, that's definitely good advice. So thank you so much, Melissa. Is there anything else that you wanted to add?
No, I really appreciate the opportunity, and I hope that you all think about other opportunities to optimize different geometric objects and see how that can come into to help you succeed in life.
Great. And can this be used with like circles and that sort of thing?
Yes, it can. It could be. I like to think about, if you start with a paper plate and you cut out a sector, kind of make a Pac-Man and fold that around to make a cone, what Pac-Man mouth cut do you need to make so that you could have a maximum ice cream cone? So lots of things that come up.
There you go. Well, thank you so much, Melissa. And thank you very much for being an exhibitor in Discovery Fest. It's been awesome to hear what you have to say. Your advice, as well as your technical knowledge, is very awesome. So thank you for everything you've done. And we want to give a special shout out to all our sponsors that make Discovery Festival possible. Again, the National Math and Science Initiative are all part of this great event we're able to put on every year. And it's because of sponsors like them and Honeywell and the others that we're able to do what we do. So we want to give a special thank you to them. This is the last day of the first week of Discovery Festival. So we'll have a whole lineup next week. So I encourage you to check out our website, discoveryfestnm, as in New Mexico, .org, to check out the upcoming exhibits. Thank you so much, and we will catch everybody later.